Hey everyone, welcome to the remote version of Physics 2001. Should definitely be interesting. Of course, there's a pandemic, so let's maybe be a little bit patient with how all this goes. I obviously am not going to have the most riveting online recordings. I'm not in the podcast midlife crisis phase of my life just yet. So this is my first time really making online recordings, and hopefully this works out okay. So as far as how we're going to run the class, the best information I have for you so far is the email that I sent out on March 10th, um, and that is how I intend to proceed moving forward. Of course, any feedback that you have would be appreciated. I'm open to trying to improve this and to try to make things that work for you. The course is going to be run online for the remainder of the semester, though even before the university announced that, it was pretty clear that was going to have to be the case because many of you were heading home. In any case, so it'll be online for the rest of the semester. I think the best way to mimic the in-class questions is the following, and this might actually even be better than what we were doing before, is send me any questions you have to my email. It would make my life a little bit easier if you referred to the slide you were on or the time in the video you were at. And what we can do is I'll post a question anonymized. I won't put your name as far as what question you had and what it related to, and I'll post the answer below, and I'm going to put that in the Google Doc that is linked to in the slide here. At some point, I will make that Google Drive folder open for you guys to see, so you can then look at the questions from all the different lectures. Um, if there are enough questions about the general organizational uh, structure of the class now, I will probably also create a Google Doc with frequently asked questions there. So please try to keep on top of your email for updates. I think most of you are probably used to this now. If you're not, you're obviously going to be soon. Please try to keep on top of your emails because that's how we're going to send updates. Okay. One thing I want you to keep in mind is that your health, your family's health, your friend's health is much more important than this class. So all of this is flexible. If you need any kind of deadline extensions or special accommodations, just let me know, and we'll work it out. Okay. So just quickly, this is a copy of the email that I sent you on March 10th. The main takeaways here are that the homeworks in pre-class are going to be the same as they were. Okay, that was already an online class, essentially anyways. I'm going to post video lectures. I think I'll be able to post them on lon-capa. I'm a little bit worried about the storage space. They'll definitely be posted on my website. For now, look for them on lon-capa. If I have to change anything, I'll let you know. I will likely try to post these on YouTube yet. I haven't done that yet, but I'll try to do that to get around any video player compatibility issues. So these are going to be saved as MP4s. I'm assuming all you guys can play an MP4, but I don't know. Yeah, mimicking in-class questions I already went over. Office hours, I want to do these remotely. So here in the email that I sent out, I said I was going to do a Zoom call. I have now set up Microsoft Team, so probably we're going to go the Teams route, but I'll send you a message related to that. I'm going to move the office hours to 1 to 2 p.m. on Wednesdays, and that's just because during my kids' nap time is probably my most reliable time. I'll be able to answer questions, in real time via video. Of course, please just send me emails if you have any questions, and we can try to resolve any questions that way as well. As for the lab, we're probably going to do what we call a dry lab. So basically, we provide you data, we provide some guidance, maybe a video on how the lab was performed, and then you work through the lab that way. The mode I think we're going to use is where we'll distribute a Word document of the labs, and you can then enter in some of your work that way, and then you'll email your lab report to your TA. So I have yet to do it, but I'll distribute a list of TA emails corresponding to the section time. So if you at least remember when your lab was, then you should at least be able to figure out what your TA email was. The midterm, we're leaning further against postponing it. Since the email was sent, the decision was made to suspend classes throughout the rest of the semester. So we're going to be doing an online exam. We're leaning right now to some kind of timed, fixed time assignment thing on lon-capa. Basically what would happen is it would lock you out of the rest of lon-capa and you'd have a fixed amount of time to complete the assignment. And we would only make it open to work on a fixed clock time. So for instance, 7 to 9 p.m. or 7 to 8 p.m., something like that. This is new for all of us, so what we're probably going to do first is post a practice exam where you can practice it. We're also, just in full disclosure, we're discussing maybe doing shorter exams and more of them or something like that. So we're still working on it, but we'll update you as that goes. Right, so and as I said in the email, thanks for being patient. Please email me with any questions, feedback. All of that would be much appreciated. So for the exams, I just want to note that probably the best thing for us to do is to reserve the regular exam time, just because you guys already had that open in your calendars or reserved, hopefully. So that's likely what we're going to do as an evening exam. Now, I understand that might not work for you because of your different family circumstances right now, so just let me know when we do send out an announcement about when the exam will be. If there's an issue for you, let me know and we can work it out. The pre-class assignments are still going to be due. Help room, I shouldn't say here. Help room, I think the way we're going to do it is you can send emails on Wednesday and Thursday, and the TAs will answer them between 6 to 9 p.m. I think that's the way we're going to go. We'll see. SI is working out an online solution as well. I don't have all the details yet. I'd like to point out that midterm 2 is in just 2 weeks. So do start to study the material that we've covered since midterm 1. And there's Christopher Wallace imploring you to do that. Okay, so just finishing up from last time, this is a top hat question we were going to do. Now, one thing I want to point out with Top Hat, obviously there's not the in-class response now. I'm not going to try to do these lectures in real time. I don't think that's going to work. What I have done is I've opened up the Top Hat questions for this lecture for review for you to quiz yourself. So what I encourage you to do with these Top Hat questions is to listen to me read the question or ignore me and read it, pause the video, try to solve it, and then start the video again, and you'll see how it's solved. Okay, so that's what I encourage you to do. So, if a space station designer wanted to mimic Earth's gravity by employing a rotating ring design, which is something people were looking into in the 50s, then astronauts would inhabit the outer ring layer at a radius of about 1 kilometer. And then that's going to rotate about the center at some velocity. So the question is, if you want to mimic Earth's gravity at a radius of 1 kilometer in a spinning ring, how fast does the outer ring layer need to be moving? So what is the transverse velocity as indicated in the figure? So take a moment, pause the video, think about it. Okay, so the answer is about 100 meters per second, which is pretty crazy. So how would you figure that out? Well, okay, you want the force at that radius to be equal to the force of gravity on the surface of the Earth. Okay, so on Earth, gravity is the mass times little g. On the space station, right, the only force that's going to really be acting on the astronaut here is the centripetal force. So your force is going to be the mass times the centripetal acceleration. So what do we need here? If you see that mg has to be equal to ma, so we need the centripetal acceleration to be equal to little g, which is 9.8 meters per second squared. You may recall the centripetal acceleration, that is the transverse velocity squared divided by the radius of the orbit. That needs to be equal to little g. We're given that the radius is 1 kilometer, so we just do a little bit of algebra, and you see that that works out to about 99 meters per second is the transverse velocity, which is about 220 miles per hour, which is pretty incredible. So this was actually looked into in the 50s. So for instance, Werner von Braun, who was a enthusiastic Nazi, to be clear, and then founded America's rocket program. He worked heavily on this. And there was also a project led by Stanford. They looked into that, and it was a similar design. So a follow-up question that the Stanford folks looked into is, what is the corresponding angular velocity here? So if you have this ring where at 1 kilometer the transverse velocity is 99 meters per second, what is the angular velocity of that rotating ring? Okay, I'm going to assume that you've paused the video and come back. So it turns out it's 0.1 radians per second. And so remember that the transverse velocity is the radius of your orbit times the angular velocity. And so that means the angular velocity is the transverse velocity divided by the radius. We have those other numbers, so we can plug that in, and we get 0.1 radians per second. We can convert that to revolutions per minute, right? There are 2 pi radians per revolution, and of course 60 seconds in a minute. So you do the conversion and you get, that's 1 revolution per minute. So if you want to read more about this, you can just Google the Stanford torus, and there's pretty interesting information online there for that. So as I mentioned at the very beginning of the lecture, rotational and linear motion are related, and that is going to be very convenient for us when we're learning these rotational motion equations. So what I'm doing here is I have a table where I have the equation for kinematics in 1 dimension and the equations for Newton's laws, so that the 1D kinematics and the dynamics equations that we went over. And I'm going to show how these apply to rotational motion. So substituting in our new quantities. So the table has in the left the linear quantity and in the right the corresponding rotational quantity. So for instance, when we want to talk about moving in 1D, the relevant dimension is the length. And the SI unit for the length is the meter. Now, as we mentioned, when we're talking about sweeping through some angle, when we're talking about rotating by some amount, then the corresponding rotational quantity is going to be the angle. And the angle is equal to the arc length divided by the radius of curvature, the radius of that circle. So the SI units here are the radian. Okay, so in rotational motion, angle is analogous to length in 1D motion. In terms of the motion itself, so in linear motion, we have a velocity, right? That's a distance over a time. In rotation, we have the angular velocity. So that's the change in angle over time. Taking that to the next step when we take the derivative of velocity versus time. So how does that velocity change over time? That's the acceleration. So change in velocity over elapsed time. And of course, in rotation, you have the angular acceleration. So that's the change in the angular velocity over time. And then in terms of inertia, so resistance to motion, in 1D kinematics, we have the mass. In rotational motion, our sort of resistance to rotational motion, or rather resistance to changes in rotational motion, that is called the moment of inertia. It's given by the variable I, and the equation for that is always going to depend on the mass times the linear extent of the object squared, but the exact formula is going to depend on the object shape, and we give you a table for that. And you would be expected to be able to use, have those formula in front of you for an exam. Now, of course, since you're taking the online exam online, you can have whatever you want in front of you. But in the in-person exam, you'd have an equation sheet and we would give you these moment of inertia formulas. Nobody expects anyone to memorize these. And if you go to the OpenStax books, you can get a preview of some of these formulae already. So figure 10.12 has some of the most common moments of inertia. So in terms of dynamics, you guys remember Newton's laws. So force is equal to mass times acceleration, the unit there being the Newton. In rotational motion, now we can take a look at the dynamics equations, look at the table above, substitute in the rotational quantity for the linear quantity. So torque is now our sort of rotational force, okay? And if force is mass times acceleration, and the moment of inertia is like our mass, and the angular acceleration is like our linear acceleration, then you can see that the torque is equal to the moment of inertia times the angular acceleration. So it's basically F equals ma, but in rotation. Okay, torque is equal to moment of inertia times angular acceleration. So now let's take a look at momentum. So momentum in 1D, right, is mass times the velocity. So now we have angular momentum. So that's in the rotational sense. That's given by capital L. And so we're going to substitute in the linear quantity or the rotational quantity into the linear quantity. So rather than mass times velocity, we have moment of inertia times the angular velocity. That's how we define angular momentum. And we're going to get practice with using all these equations. Okay, so if you want to find the tangential motion or the transverse motion corresponding to a given rotational motion, then these are the equations that you'd like to have. So this slide is kind of a good, just general cheat sheet itself for rotational motion. So the arc length that you cover when you sweep through some angle is going to be equal to the radius of that circle times the change in angle. The tangential velocity or transverse velocity, this is equal to the radius of that circle times the angular velocity. The transverse acceleration is equal to the radius of the circle times the angular acceleration. And these are all things that we've covered so far, except for maybe tangential acceleration. So remember the names of these variables. The S is arc length, T is tangential or transverse velocity, or sorry, V sub T, and A sub T is the tangential or transverse acceleration. Okay, so let's put some of this into practice that we just learned. So we have an object. It starts at rest and it undergoes an average angular acceleration of 0.5 radians per second for 10 seconds. So the question is, what is the angular speed after 10 seconds? So it starts at rest. It's going to begin rotating, undergoing an average angular acceleration of 0.5 radians per second squared. It's going to do that for 10 seconds. What is the angular speed, the angular velocity after 10 seconds? Okay, so I'm going to assume you paused and now you're back. So that is 5 radians per second. And this is relatively straightforward. The angular acceleration is the change in the angular velocity divided by the elapsed time. The change, so we do some algebra, we see the change in the angular velocity is equal to the angular acceleration times the elapsed time. And we can just plug in the information we have, 0.5 radians per second squared times 10 seconds. And that is known to its friends as 5 radians per second. So that's the change in the angular velocity. Since the initial was 0, then of course the final is just going to be that 5 radians per second. Okay, so this one's a conceptual question here. So we have 3 erasers sitting on a turntable. So you're basically looking from above onto a turntable, or if you don't know what that is, I don't know, it's like a CD player or a record player or a Lazy Susan, something like that. Okay, so you're looking from above towards the turntable, and these 3 objects are erasers that are sitting on there. So eraser A is near the edge, eraser C is closest to the center, and eraser B is in the middle. So this surface is not frictionless. So these objects there is some friction there. So starting from rest, the turntable is going to slowly accelerate. It's going to begin spinning faster and faster and faster and faster. So the question is, which eraser is going to fly off of the edge first? Or are they all going to do it at the same time? Okay, so eraser A is going to fly off first. Why is that? It's not just because it's the closest, it's because the centripetal force there is going to be the largest. Right, so remember that F is equal to ma, force is equal to mass times acceleration. The centripetal acceleration is the radius of our circle that you're moving in, times the angular velocity squared. And the angular velocity is going to be the same for erasers A, B, and C, right? They're all on the turntable, and that's a rigid object. So the whole rigid object is rotating at the same rate, of course. Otherwise, it would be breaking apart. So the angular velocity is the same for all of these, but the radius is the largest for A, the distance from the center of the turntable, and so it's going to have the greatest centripetal acceleration, and therefore there's going to be the greatest centripetal force, and so that's going to require the greatest force to stay moving in a circle. So what you would see happen is if we assume the friction between the eraser and the turntable is the same for A, B, and C, the turntable is going to begin to rotate. At first, nothing's going to move. Then first, A is going to slide outward because the centripetal force is going to exceed the maximum static friction force. Then a little bit later, B is going to begin to slide. And then finally, when you're rotating extremely fast, the C will finally also eventually move because the centripetal force will presumably eventually overcome the static friction force. So for instance, this is a fun example of that, right? You guys might remember in a merry-go-round when you went on these as a kid, right? If you wanted to be able to stay in the merry-go-round, obviously you want to stay as close to the center of this thing as you can. So with these morons here, what happens is you notice the guy who gets flung out, he isn't able to keep his center of gravity close to the center of the merry-go-round. So once he starts to lean back a little bit, the centripetal force gets a lot larger, right? And he's then flung out from the merry-go-round. The guy who's able to keep leaning inward, he is able to maintain himself inside the merry-go-round. Okay, so now let's talk a little bit about rolling without slipping. So we're not going to cover rolling with slipping, that complicates things. But when we have rolling without slipping, then of course the linear distance that you travel for a given rotation, that's just going to be equal to the arc length between the initial and final points of contact on the surface of the wheel. This comes from our definition of an angle. The angle is the arc length divided by the radius of curvature, and so then it makes sense that that's the distance that you cover. So the linear distance is just going to be equal to the arc length. So that's the radius of your circle times the change in angle. And that's the change in angle that you've undergone as you've rotated. So note, theta, the angle here, it needs to be in radians, okay? This equation only makes any sense if you're in radians. So the translational velocity, so this is your linear motion velocity. So when you have a wheel that's rolling, right, if you were just to look at the axle of the wheel, it's moving forward at some velocity. That is the translational velocity. So that's going to be related to your rotation rate by dividing the relationship for distance divided by time. So your transverse velocity or tangential velocity, it's equal to the radius of the circle times the angular velocity. So that's how we get that equation. And then similarly for acceleration, you divide by time and you get that the tangential or transverse acceleration is equal to the radius times the angular acceleration. Okay, so what's cool is, you could use these relationships, right, plus your tachometer and your speedometer readings to find the gear ratio between your crankshaft and your tires. right? So long as you know your tire radius. So you can take advantage of this equation that the transverse velocity is equal to the radius of curvature times your angular acceleration to figure out this gear ratio, right? So for instance, if your gear ratio, um, so the gear ratio I should explain, it basically says for every revolution of your crankshaft in your engine, how many revolutions does your tires do? How many revolutions do they do? So if the ratio were 1, so for every revolution of your crankshaft, you get 1 revolution of your tire, then when your tachometer in your car reads 2,000 revolutions per minute, that equals roughly close to 200 radians per second at your tires. So if you have a 0.25 meter radius tire, close enough to true, then your velocity is going to be about 50 meters per second. So you go 112 miles per hour. So we can compare then to the actual gear ratio for a Corvette manual transmission. And you can see that indeed when you get to about 4th gear, you have your gear ratio is 1. So for every revolution of your crankshaft, you get 1 of your tire. You know, I've never driven a Corvette. Maybe you have. I've ridden in one. So I'd say 4th gear, yeah, you're getting close to that 100 mile per hour range. Maybe really it's in 5th gear. So in any case, the point is that this works. So you can convert between rotational motion and translational motion using these equations here. So let's go ahead and do that. So if we have a pulley that has a radius of a decimeter, which is 0.1 meters, if that has a string wrapped around the rim, so imagine sort of like a yo-yo, if the pulley is rotating on a fixed axis at an angular speed of 0.5 radians per second, what is the length of the string that comes off the reel in 10 seconds? So a better analogy might be a fishing reel. Okay, so you have this pulley, 0.1 meter radius, you have a string wrapped around it. The pulley's rotating, it's basically unspooling the string. It's rotating at 0.5 radians per second. In 10 seconds, how much string comes off of the spool? So I'm going to assume you've paused, thought about it, answered it, and you'll find that it's 0.5 meters of string. Okay, so the angular velocity, this is the change in angle divided by the elapsed time. So that means the angle that you swept through over some elapsed time is then going to be equal to 0.5 radians per second times 10 seconds. It's 5 radians. Okay, so we know what angle we've covered. Now we need to convert that into the arc length that has been basically unraveled. So the change in angle, right? This is the change in arc length divided by the radius. So our definition of arc length is radius times the change in angle, and you can figure out that's 0.5 meters. So yeah, so the linear distance that that has been traveled by your string, you can think of it that way, is equal to the arc length. And believe it or not, this is actually practical. A few years ago now, this idea of converting between linear and translational motion was used to come up with a pretty innovative medical device. So you guys might remember the toy whirligig. So it's the object this person is holding. So the one they're holding is very special. So the idea is that you take, this person would put their hands closer together, and then they would pull them apart. And once you get this thing spinning, with the disc in the center spinning, when you move your hands closer together, some of the string is coiled up, and when you pull further apart, that string is unspooled basically, and it's a fun toy. It spins around. So what this group realized is that you could create a centrifuge where you basically pump your hands back and forth for several minutes, and you now can do life-saving medical tests out in areas where there's little to no electricity, which is kind of amazing. So believe it or not, as useless as a lot of this may seem or irrelevant to you, in this case, you know, the conversion between rotational and linear motion was actually critical to solving this problem. And right, so here's the whirligig in action. So you see them pumping their hands. The string is coiled up and then unraveled. Okay, so now let's consider Newton's laws in rotational motion in a little bit more detail. So first, let's just consider we have a puck, okay, on an ice rink or a frictionless tabletop, so that disc there, that circle, is like a hockey puck. And let's say it's on ice, so it's frictionless. And it's attached to a post that is a distance r away. So that's going to enforce our circular path with radius r. And we're going to say that it's attached to this post by a rod with basically no mass or negligible mass. Okay, so that's just to enforce this radius r. So the transverse force that is plotted here, the tangential force, that's going to be equal to the mass times the tangential acceleration. F is still equal to ma. It's always equal to ma. And we can now substitute in some of the things we know. We know that the transverse acceleration is equal to the radius of that circular orbit times the angular acceleration. And what we can do is we'll multiply each side of the equation, so we're going to multiply the left and the right sides by r, this radius of curvature. So you can see why we're doing that. You guys probably recognize the force times the distance. That's a torque, tau. So the torque is equal to the mass times the radius squared times the angular acceleration. And we'll now define this quantity, mass times radius squared, as the moment of inertia. So rather now than F equals ma, we have torque is equal to moment of inertia times angular acceleration. Now, one thing I want to make clear is this specific formula for the moment of inertia, the mass times the distance squared, this specific formula only applies for an object at some distance, okay, like a puck orbiting in some circular radius. In general, the moment of inertia formula is going to depend on the object's geometry, okay? And so we'll see that the formulae become slightly different for different objects that you have. So for a point mass, the moment of inertia is the mass times the radius of the circle squared. Okay, that's only true for a point. Now, if you get extended objects, it gets much more complicated. So this is figure 10.12 from the OpenStax book, and these are some of the more common geometries that you're going to see. And anytime you would need these, we would give you the formula. So what's indicated in these figures is the axis of rotation. And so the object is going to spin about that axis of rotation. And then you have objects of different geometry. So for instance, if I have a solid sphere and I'm rotating about our axis of rotation, then the moment of inertia isn't mr squared, it's 2/5 times mr squared. If instead of a solid sphere, I have a thin spherical shell, so this is like a hollow object, there's just mass on the outer radius here, then the moment of inertia is 2/3 times mr squared. And you can see this is different for different objects. So for instance, let's take a solid cylinder and we're going to spin it about this axis of rotation. Then the moment of inertia is 1/2 mr squared. If instead you take a solid cylinder and you spin it about this axis of rotation, you get something a little bit more complicated. Okay, and so it depends not only on the geometry of the object, but also where your rotation axis is. In general, calculating these moments of inertia can get kind of complicated. The way you'd actually figure out these coefficients here, so what fraction you put in front of mr squared, you wind up having to integrate over the mass of the object. You basically integrate this mr squared over the geometry of the object, and we're not going to do that in this class, right? This isn't a calculus-based class, but that's how you'd solve it. For our purposes, it's enough to have this nice cheat sheet where someone already did the work for us. Okay, so let's take some of this knowledge and put it to practice here. So we have three pucks, or you can consider them point masses. They're attached to these massless rods that fix them at a given radius of curvature. So they're a given radius r from the center of a circle. And we apply the same force to each of these objects. So the question is, which system is going to have the greatest moment of inertia? It's going to be 1, 2, or 3. So I'm going to assume that you guys have paused the video and you're back. You'll see that it's actually system 3, right, is going to have the greatest moment of inertia. So one important thing here is the force is applied at the same distance from the center of the circle, right? So if it's the same force at the same distance, then you're going to have the same torque. It's a key point. And our point objects, they have a moment of inertia of a mass times radius squared. So let's calculate these moments of inertia. So for object 1, the moment of inertia is the mass times the radius squared. Right, simple enough. For object 2, you see the mass of this puck is twice the mass of the puck in system 1, and also twice the mass of the puck in system 2. So we're going to call that 2m. So the moment of inertia here is 2m r squared. And in system 3, the moment of inertia is going to be m times the distance from the center of the circle, which here is 2r, right? So m 2r squared. And when we square 2r, then we get 4 times r squared. So the moment of inertia of puck 3 is 4 times mr squared. And then we can just rank these. We see that the moment of inertia of 3 is greater than 2 is greater than 1. And so then system 3 has the greatest moment of inertia. So remember that the key qualitative takeaway is the moment of inertia depends on the mass of the object, its mass distribution, and its location. Okay, so that is the key sort of concept going on here. So let's take the same system, but now what I want to know is which system has the greatest angular acceleration. So you know the moment of inertia of all these objects, you know where the force is applied, and you know it's the same force. Which one's going to have the greatest angular acceleration? And the key formula here, right, is Newton's laws, but for rotational motion. So rather than F equals ma, you have tau is equal to I alpha. Torque is equal to moment of inertia times angular acceleration. I'm going to assume you've paused and you're back. And you'll see that it's system 1 is going to have the greatest angular acceleration. So we already went through the business of figuring out the moment of inertia for each of these 3 objects. And we need to keep in mind that the torque is equal to I alpha. And the torque here is going to be the same for all of these because I have the same force and it's applied at the same distance from the axis of rotation. So torque's the same. The angular acceleration is the torque divided by the moment of inertia. And so then the system with the smallest moment of inertia is going to have the smallest denominator and therefore the greatest overall number here, right? So if I have a smaller number in the denominator, that's going to lead to a bigger fraction, basically. So the angular acceleration is going to be maximized for the system with the smallest moment of inertia, which is system 1. So that's going to have the greatest angular acceleration. So moment of inertia, this is resistance to rotation given some applied torque. Or more accurately, it's the resistance to the change in rotation given some applied torque, which is just like how inertia, right, the mass of an object, inertia is the resistance to motion or change in motion given an applied force. So moment of inertia, right, this is given by the variable capital I. This is our resistance to rotational motion, resistance to changes in rotational motion. Again, it depends on the mass distribution, and it depends on the mass distribution with respect to the rotation axis. So it's going to change even for the same exact object, if I change where my rotation axis is, I'm going to change the moment of inertia. And that's just a note about how you could solve for it in using calculus. We're not going to do that. A general concept here, what's something qualitatively you should know, is that the more concentrated the mass of an object is toward the rotation axis, the lower your moment of inertia. Okay. So we can combine this also for compound objects, which is going to be really useful. So what do I mean by that? So for instance, let's take a golf club. So for a golf club, you basically have a thin rod, that's the shaft of the golf club, and then you basically have a point mass, is the body of the club. Or if you want to be really precise, you'd use a shell of mass at some distance. And so we combine this using the so-called parallel axis theorem. So what the parallel axis theorem is the following. So if I take an object, let's take this funny thing here, has some mass distribution, then the moment of inertia for this blue object with respect to the axis of rotation that we're calling z prime here, this leftward arrow, the moment of inertia of the blue object for this setup is equal to the moment of inertia for the object itself. Okay, so whatever the moment of inertia for this dude is, plus the mass of that object times the distance of its center of gravity from the axis of rotation. So maybe we can think of a simpler case. Let's imagine that we have a thin spherical shell and it is some distance d. Its center of that shell is some distance d from our axis of rotation. Then for that spherical shell, the moment of inertia for that particular setup is still going to be 2/3 mr squared. Okay, it's still going to be this 2/3 mr squared plus the mass of the spherical shell times the distance between its center and that new axis of rotation. Okay. So if you want to think about everyday life, where this moment of inertia comes into play, well, everyday life if you play baseball, or if your kid or cousin or nephew or whatever plays baseball, the moment of inertia is actually given by the swing weight index of a baseball bat. So you might know with baseball bats, you can buy a wooden baseball bat or you can buy an aluminum baseball bat, and you can get them of different shapes. And what you'll often see with aluminum or composite bats is they'll give you a swing weight index. And so, for instance, they'll tell you, hey, the actual weight of this bat is 23 ounces, but we've distributed the mass such that it feels like you're swinging a 28-ounce traditional wooden baseball bat. Okay, so for instance, the picture here, we're comparing aluminum to wood bats. So the red line, it indicates the center of mass or your center of gravity. And so what's done often with the aluminum bats is in this example, the center of gravity is moved a little bit closer to the axis of rotation, which is sort of near this handle end of the bat. And so we have a heavier bat overall. It's 27 ounces, but it swings like some of these lighter bats, these ones that weigh less, because you've moved that center of gravity a little bit closer. Okay, so for instance, you have a table here of your different swing weight index bats for different composite materials. You don't need to memorize that. I just think it's kind of an interesting fact. Okay, so let's remind ourselves here of some torque things that we learned before and bring in our knowledge now about moment of inertia and angular acceleration. So we have this object here. This is a disk. The black circle is the axis of rotation, and we have forces B and A. The length of the arrow indicates the magnitude of the force, roughly, and of course the arrow location indicates where it's applied. So we have two forces exerted on a wheel, has a fixed axle at the center. Force A is going to be applied at the rim. Force B is applied halfway between the axle and the rim. And the magnitude of force A is 1/2 the magnitude of force B. So the question is, which best describes the direction of the angular acceleration here? And keep in mind that our wheel here is basically a disk, and we're rotating that about some axis. Okay, so the angular acceleration here is going to be 0. So why is that? Torque is the moment of inertia times the angular acceleration. We now need to calculate the torque for each scenario. So the torque B is equal to force B times the radius of the rim divided by 2. This is negative because you're applying the rotation would be in a clockwise direction, and that's a negative torque. The torque for force A is going to be force A times the radius, the rim radius. We established that force A is 1/2 the magnitude of force B. So then that is going to be equal to force B over 2 times the rim radius, which is just minus torque B. So then the net torque is going to be torque A plus torque B, and those are going to be equal to 0 because they're equal in magnitude but opposite in direction. So if your net torque is 0, then your angular acceleration is going to be 0. Because again, tau is equal to I alpha, so alpha is equal to tau over I, and then if tau is 0, alpha is going to be 0. Okay, so another question. Let's say we have a solid wood cylinder and we have an aluminum ring. Okay, they're both located at the top of a ramp. Okay, they're sitting there ready to roll, and we release them at the same time. So the question is, which one of these objects is going to roll to the bottom of the ramp first? So is it going to be the solid cylinder? Is it going to be the ring? Are they going to tie? Is it going to depend on the mass? So is the heavier one going to make it to the bottom first? Is the lighter one, or is there just not enough information? And the moments of inertia for these objects are in the bottom right hand corner of the slide. So take a moment and think about it. I'm going to assume that you've paused, worked on this, and come back. And you see that it is the solid cylinder. So amazingly enough, you do have enough information to solve this, and you can see that it's the solid cylinder. If you want proof, here is a demo here. It's actually funny, people razz me for using GIFs all the time, some of the other lecturers did, and now that we're all online, I guess the joke's on them. So you see we have a solid wood cylinder and we have an aluminum ring. This guy is in slow motion, releasing these at the same time. And you can see that the wood cylinder wins, right? So why is that? Well, the ring's mass is concentrated further from the rotation axis than the cylinder, right? That's obvious. The ring is hollow, so all its mass is out near the radius of the ring. So therefore, our ring is going to have a larger rotational inertia, right? And what that means is that the ring is going to be more resistant to rolling. So therefore, our cylinder is going to start rolling earlier, right? That solid wood cylinder is going to start rolling earlier, and it's going to make it to the bottom of the ramp first, okay? And if you want to know, like, why don't we need to know the masses, it's because the mass is going to cancel, right? So your gravity is what's accelerating these objects downward. The force of gravity is proportional to the mass of the object. The moment of inertia is also proportional to the mass. So the mass is going to cancel in motion, so we don't need to know the mass of the objects. So it's really just where your mass is concentrated, what's your moment of inertia. And the cylinder has a greater moment of inertia. It's going to be more resistant to rolling. Okay, so this is basically related to the reason that a broom is a whole lot easier to balance if you have the brush end upward. Okay, so if the axis of rotation for the broom is the palm of your hand, then you're going to maximize the moment of inertia by moving the brush opposite your hand. It's going to be more resistant to rotating. Okay, so let's now consider another sort of practical, if not everyday life object, a often encountered object, pulleys. So previously, when we were talking about tension, we used pulleys to redirect our tension. And we always went out of our way to note that they were massless. So why did we do that? Well, that's because your pulley has a rotational inertia. So aside from the fact that there's going to be friction in the pulley, there's also going to be a rotational inertia. It's going to resist rolling. Okay, so if we hang a weight from a rope, and that rope is wrapped around a massive pulley, that's going to behave similarly, right, to a weight hung from a rope that's attached to a mass on a frictionless table. Okay, so think about that. If we have a weight and we hang it from a rope that's wrapped around a pulley that has some mass, that's now going to be very similar to connecting your weight to a mass that's on a frictionless table and letting that fall. Okay, so pictorially that means that the situation on the left, where our pulley has some mass, is going to be very similar to the situation on the right. So the pulley has resistance to rotation, just like mass A on the right has some resistance to moving linearly. Okay. So for instance, let's say we have a 0.5 kilogram weight, and we're going to hang that from a frictionless pulley, but the pulley has a mass of 1.5 kilograms, and the pulley has a radius of 0.1 meters. So the question that we want to answer is, how long does it take for the mass to fall 1 meter? Now, if the pulley had no mass, this would just be straightforward free fall. But the pulley has mass now, so there's going to be a resistance to rotation. Okay, so how do we deal with this? We basically need the acceleration of the mass, and we're going to turn this into a 1D kinematics problem. So what we can do is we can use F is equal to ma. So remember that F in F equals to ma is the sum of the forces. It's the net force. Okay, so the sum of the forces here, the net force, is equal to the downward force of gravity on our mass, it's just mg, minus the tension. So there's some tension between pulling upward on that mass, on that 0.5 kilogram mass. And that is equal to the mass of the weight times the acceleration. Okay, so then we can solve for the linear acceleration of our mass. That's equal to little g minus the tension divided by the mass. So that's all well and good, but we don't know the tension here, right? So we need to figure that out. So, okay, how are we going to do this? So the way we work to get the acceleration of our 0.5 kilogram mass is we are going to take advantage of the relation to rotational motion. So we know that the linear acceleration of our mass, so it's linear acceleration downwards, is equal to the radius of the pulley times the angular acceleration. So this is because the string here, right? Remember that as we unspool the string, the length of string that is unspooled, that is equal to the arc length that is traversed by rotating the pulley by some amount. Okay, so that's how we figure out that the linear acceleration, the linear downward acceleration of the mass is equal to the radius of the pulley times the angular acceleration. All right, and the torque that is applied by our mass, that is equal to the moment of inertia of the pulley times the angular acceleration. Right? Sorry, I know this is a lot here, but that torque, right, is going to be equal to the radius times the tension. Okay, so we have two relationships for torque. So one is related to the rotational motion of the pulley. The other is the torque applied basically by the weight. So this is a force times the distance. Okay, So we have some tension force basically applied by the weight. That is a distance r from the center of the pulley. Okay, so that torque that's applied here is equal to the same torque that's causing the pulley to rotate. So that's why we know that I alpha is equal to F times R, or in this case, tension times the radius of the pulley. Because the pulley is a disk, the moment of inertia is 1/2 times the mass times the radius of the pulley squared. So we can solve this algebraic equation and get that the angular acceleration is then equal to the torque that we're applying, okay, divided by the moment of inertia of the pulley. And so that is equal to 2 times the tension of the mass, the tension caused by the mass, divided by the mass of the pulley times its radius. Okay, so chugging through all of this, then the linear downward acceleration of the mass is equal to the radius of the pulley times the angular acceleration, and that is equal to 2 times the tension divided by the mass. So we are going to set our accelerations equal. So we've solved for the acceleration in this step here, and we've solved for the acceleration above. So we're going to set these two equal. So we have acceleration is equal to little g minus tension divided by mass of the weight. We know that that acceleration is equal to the one we just solved for, which is 2 times the tension divided by the mass of the pulley. Okay, so we're setting those two equal to each other here. That's, sorry, I lost my mouse. So this g minus t over m is equal to 2t over m. Okay, so we do this algebra, and we find that the tension is equal to little g times the mass of the weight times the mass of the pulley divided by the mass of the pulley plus 2 times the mass of the weight. Substituting all of this, we get that the linear acceleration of the mass is 2 times little g times the mass of the weight divided by the mass of the pulley plus 2 times the mass of the weight. So all of this was a lot to get to. So you might just want to write these equations down because we're not going to give you something more complicated than this. So for the situation where you have a mass attached to a string and the string is wrapped around a pulley, these equations are going to be true. Okay, the tension in the string is going to be equal to this equation here. The linear downward acceleration of the mass is going to be equal to this equation listed here. Okay, so just write those down, and that is true. You of course can solve it using the information that you know for your dynamics in 1D and in rotation, but this is a lot of work, so maybe just consider writing these down. So now finally, if we want to figure out how long it takes for the mass to fall 1 meter downwards, we can then just use our good old 1D kinematics equations. We know what distance we've traversed over a given time. We're starting out assuming our initial vertical position is 0, and it starts from rest, so the initial vertical velocity is 0. So then the time is then the time it takes to cover some distance is equal to the square root of 2 times that distance divided by that linear acceleration. And we've solved for the linear acceleration after all that work, and we get that it takes 0.7 seconds to go down 1 meter. So again, a couple of these equations you're just going to want to have written down. It's a lot of work to get there. So what happens if we have multiple objects? So if we have a so-called compound object, then we can add together the moments of inertia. So let's take an example. We have a disk, that's that purple circle, and we're going to put 2 point masses on top. That's the 2 blue circles. And they're all spinning about the center of the disk. Okay, so what's the moment of inertia for this compound object? Well, we can just add the moments of inertia together. So the total moment of inertia for this whole ball of wax here is the moment of inertia for a cylinder, so that's going to be the purple disk, plus the moment of inertia for a point mass, that's blue object A, plus the moment of inertia for point mass B, which is the blue object B. So then we can write down the equations for these. We know that the moment of inertia for a disk is 1/2 times the mass of the disk times the radius of the disk squared. And for the point masses, it's their mass times their radius from the circle squared. So that's the equation. And so pictorially, basically, if you have the moment of inertia for the disk plus for point mass A plus for point mass B, that is equal to the moment of inertia for the whole scenario here. Okay, so that's how you deal with multiple or so-called compound objects. Okay, so let's put this into practice in a qualitative scenario. So each red dot here is going to be a 1 kilogram mass on a turntable. So the question is, which of the 3 turntables here, A, B, or C, requires the least torque to achieve a given angular velocity after some fixed amount of time? Okay, so you're going to apply a torque to each of these. Which one's going to require the least torque to achieve a given angular velocity after a fixed amount of time? So I'm going to assume you've paused, thought about it, and come back, and you'll see that it's scenario C, right? So the qualitatively, right, the mass is concentrated towards the axis of rotation. So this is going to have the smallest moment of inertia, and therefore it's going to require the least amount of torque to achieve a given angular acceleration. So just like F is equal to ma, tau is equal to I alpha. So then the angular acceleration is the torque divided by the moment of inertia. And so the smallest denominator is going to give you the biggest fraction there, right? So if you have the smallest moment of inertia, that's going to require the least amount of torque to achieve a given angular acceleration. In situation C, right, our mass is really concentrated towards the rotation axis, so it's going to have the smallest moment of inertia, and therefore that's going to accelerate the quickest for a given torque. And then it's going to achieve that given rotational velocity first, right? You could, of course, calculate the moment of inertia for this scenario. As we covered previously, it's a compound object. So we have the gray disk has some moment of inertia, and then we have 3 point masses. So that's how we would calculate it here. Okay, so let's now cover a different rotational quantity. So just like we have kinetic energy in translational motion, so linear motion, there's kinetic energy associated with rotation, which isn't too surprising. So we can, amazingly, just like before where we covered our 1D equations and we said, hey, there are analogous rotational equations, same business here. So in kinetic energy for translational motion, you have 1/2 mv squared, 1/2 times the mass of an object, times its linear velocity squared. For rotation, we just sub in those quantities. So the mass, instead of mass, we now use moment of inertia. Instead of linear velocity, we now use angular velocity. So the kinetic energy for rotation is 1/2 times the moment of inertia times the angular velocity squared. So a rolling object, for instance, like a bicycle wheel, this object is going to have both translational and rotational kinetic energy. So the total kinetic energy for a rolling object is that translational kinetic energy plus the rotational kinetic energy. So if I have a wheel rolling along the road, then the kinetic energy for that wheel is 1/2 mv squared. So this is the linear velocity squared times the mass of that object times 1/2. And we add to that the rotational kinetic energy, 1/2 times the moment of inertia of that wheel times its angular velocity squared. What does this mean? This is interesting, right? This means we can use rotation to actually store energy, right? So we can, if we have a rolling object or a rotating object, it stores some kinetic energy. And this is used to smooth out power availability for intermittent power sources. So believe it or not, anytime you guys encounter this most days, or any day you drive a car, you encounter this. So this is called a flywheel in an engine. So for instance, if you guys have ever engaged in pottery, this is not an everyday example, but it is a cool example. In, in a pottery wheel, what you have is a pedal that you pump, and that pedal then, through a system of gears, causes the wheel to rotate. Okay, so the wooden wheel up top here, this is where you place your clay. But in the pottery wheel, you have this big old honking metal stone down there. And the reason that you have that metal stone is when you pump the pottery wheel with your foot, you'll spin that stone. And once you get it going, it wants to keep going that way, right? It has a bunch of kinetic energy stored in that wheel. If you stop pumping, it will take some time to spin down. And so what you can do is once you get this thing pumped up, it's going to be relatively smoothly spinning, okay? And so it's going to store energy, and it's going to keep a basically constant rotation rate here. If you didn't have the heavy stone, your rotation rate would change based on whether you were pumping or not. That would be not good. Okay, so an example here is an engine flywheel. So on an engine, this is a pretty awesome example that this person put together. We have an engine here. There are these different pistons. Those are basically the black things there. You see the pistons are pumping in and out, and they're causing the crankshaft to rotate. So on the left, we have a flywheel. That's that big brass disc. And so you're only intermittently pumping, right? The pistons are going in and out, in and out. They're not constantly supplying power, they're just intermittently doing it. And you see the engine is moving smoothly here. So now let's take the same engine and remove the flywheel. And the problem is it's power is only being applied intermittently. This thing, the disc is basically kind of spinning the knot, spinning the knot, spinning the knot, and the engine more or less just doesn't run. And so you need a flywheel to keep an engine going. And if you want to hear the explanation and watch the video, that link is here. Okay, so the upshot from this is that what you really need to know is rotational motion has kinetic energy, all right? And that's a way you can store energy. And if you have a rolling object, an object that's linearly moving and rotating, then the total energy is the translational motion, so the linear kinetic energy that you all know and love, plus the rotational kinetic energy. Okay, so let's put this into practice. So an engineer, they've designed a flywheel for a hybrid vehicle, and this is a real example, that's used to store energy by engaging the engine while braking. Okay, so the idea is that while you brake, a flywheel is going to be engaged and the engine is going to be used to spin up this flywheel. Okay, so the maximum rotational velocity of our flywheel, okay, it's of course going to be limited by the strength of your chosen material, right? You can only spin it so fast or it'll bust apart. So the engineer, what they want to do is they want to maximize the power storage capability of this flywheel, right? You want to be able to store as much energy as possible. So compared to some nominal design, the question is, should they choose a material that has twice as much mass, or do they want to choose a material that has twice as high of a maximum rotational velocity? So they have to choose between something that has 2 times larger mass or something that can sustain 2 times the rotational velocity. Which object would they go with if they want to maximize that energy that can be stored by the flywheel? So assume that you've paused, you've thought about it, and you've answered the question. So what you'll find is that if you double the maximum rotational velocity, that's going to be what you want to go with if you want to maximize that kinetic energy storage. And the reason is that rotational kinetic energy, right, that's equal to the moment of inertia times the angular velocity squared. The moment of inertia of an object is always going to be proportional to the mass times its linear extent squared. Okay, so the moment of inertia is linearly proportional to the mass, and that means the kinetic energy storage is linearly proportional to the mass, whereas the kinetic energy is proportional to the angular velocity squared. All right. So then if you double the mass, right, you're just going to double the moment of inertia. Okay, so you'll then double the kinetic energy. But if you double the angular velocity, then you're going to quadruple the kinetic energy, right? Because you're going to take 2 squared. So then you would want to, in this case, go with the scenario where you can quadruple that kinetic energy. So for instance, in these flywheel designs, that's why often you would go with a carbon fiber type rim, because carbon fiber is very strong. It can sustain a rather high um, uh, angular velocity, right? So that you're gonna need a very fast rotation rate until you rip that carbon apart from the centripetal force. So the carbon fiber doesn't have that much mass, for instance, like steel or lead or tungsten, but it can sustain a very high rotational velocity. So that's why you're going to go with that for your flywheel. Okay, so that brings this lecture to an end. Thank you for sticking with this if you did. Please give me any feedback would be much appreciated. Again, apologies that the audio quality isn't really the highest. I'm doing my best, and I'll continue to try to experiment with things to make this better. If you have any tips, if you're a hobbyist podcaster or something like that, then feel free to send them. That'd be great. Um, Otherwise, I'll talk to you next time. And again, please keep an eye out in your emails for any announcements. Things are kind of fluid here, right? And I'll do my best, and I hope you can do the same. One final reminder about if you need any kind of extension, right? This is a strange time for everybody, so if you have some trouble, you don't really need to explain to me in detail what it is. Just let me know, hey, Zach, I have an issue. I need extra time. Um, just some simple explanation, and I can make accommodations, right? I think let's put this all in perspective. Physics 2001 is not all that important in the big scheme of life. So do let me know if you need any kind of accommodations. Okay, so I'll talk to you next time.